Okay, good morning. What I thought I'd do for this last lecture is, so I want to finish up a couple of loose ends from last time about topological insulators. In particular, I want to tell you what's special about the surface of a topological insulator. And that'll lead into a discussion of topological superconductivity. So I'll say a little bit about superconductivity, Majorana, Kitaev, and a little bit about sort of generalizations of this topological band theory idea that I think you'll probably hear a little bit more about next week. So let me just start with the surface of a topological insulator. So remember, we talked about a topological insulator yesterday, and I think Zahid and Vidya also talked a little bit about this. And so I just want to emphasize that this surface of a topological insulator, which has sort of an odd number or a single Dirac cone, is a very special thing. So with time reversal symmetry, it's something that can only exist on the surface of a three-dimensional system. Okay, and it has this sort of correlation between the spin and the charge because the direction in which the electrons are going in is sort of correlated with the spin. Okay, and so there's a sense in which a charge current is the same thing as a spin density, and a spin current is the same thing as a charge density in these helical surface states. And the other sort of important feature that they have is the fact that when you go around this Dirac point, you pick up my favorite minus sign. And that pi Berry phase sort of endows these electrons with a very robust property, which means that you can't localize them. Okay, and so this is something that you can see sort of if you do perturbation theory if you do weak disorder, then there's a classic calculation one can do to calculate the sort of first correction due to localization. Okay, and so this is called weak localization. And what you find is that due to this pi Berry phase, the sign of the weak localization correction is negative. So instead of driving you towards localization, it drives you towards being a better conductor. Okay, but in fact, as I explained last time, it's even better than that. Even if you have strong disorder, these surface states are impossible to localize. And again, it's the same argument that I showed you last time, which is that if you put the surface on with periodic boundary conditions, then you can show that when you thread a flux, the surface states have to sort of reconnect with each other, which means that it's impossible for the surface states to not know about the boundary condition, which means they have to be extended. Okay, so this is a feature of these surface states. Okay, so but what I want to talk about a little bit now is the interesting things that can happen if you destroy the surface states. Okay, so this degeneracy between the conduction band and the valence band is protected by symmetry. Okay, by time reversal symmetry. But you can ask, well, what could happen if I break that symmetry? And so interesting things can happen. In particularly, if you break time reversal symmetry, then you get something that's sort of like a quantum Hall state, which is interesting. Okay, and in addition, of course, in this sort of band theory, I've implicitly assumed that charge is conserved. Okay, but if you make it into a superconductor, then you violate the conservation. The conservation of charge is spontaneously broken, and then in the superconducting state, you can also open up a gap, and this superconducting surface state is also something that is interesting. Now, so actually, you can ask the question: well, let's suppose I keep both, the charge conservation, the U1 gauge symmetry, and I keep time reversal symmetry. Is it possible to open up a gap at the surface in that case? Okay, and without interactions, the answer is no. Okay, so in the context of this sort of topological band theory, where we're saying we're connected to states where you can turn the interactions off, then it's impossible to to open up a gap in these surface states. But if you allow yourself to think about strongly interacting states, then it turns out it is possible. And so there's an interesting question of what a symmetry-preserving gap state would be, and it turns out that it has to have an intrinsic topological order that's sort of similar to a non-abelian fractional quantum Hall state. Okay, and so hopefully, I'm not going to go into this in very much detail, but at the end, hopefully if there's time, I'll mention a little bit about what this is about. Okay, so let's talk about the simple thing first, which is let's imagine you break time reversal symmetry, and the simplest way to break time reversal symmetry is just to add a magnetic field, perpendicular magnetic field. So now we're back to doing the quantum Hall effect, the integer quantum Hall effect problem, and so there's a good homework problem if you have never done it before, which is to calculate the Landau level spectrum for Dirac electrons. Okay, and so that's not hard to do. It's almost exactly the same as the sort of classic Landau level problem in a parabolic band structure. So all you need to do is to take the Dirac Hamiltonian and square it. Okay, and then it turns into a quadratic a band, and then you can do the same calculation you did before. But what you learn when you do that, though, is that the spectrum of Landau levels for Dirac electrons has this magic state exactly at 0. Okay, so this is 0 Landau level, and then the Landau levels come out like square root of n. Okay, now. So this 0 level, so you can see that this spectrum here sort of can have a particle hole type symmetry. Okay, and so this gives you something interesting, because you know that the Hall conductivity, if you change the Fermi energy crossing one of the Landau levels, then the Hall conductivity has to change by E squared over H. Okay, that's the integer quantum Hall effect. Every time you cross a Landau level, the Hall conductivity changes by E squared over H. But because you have this particle hole symmetry, what you expect is that, if I change the sign of the Fermi energy, I should change the sign of sigma xy. And so that means that if I go from here to here, then the Hall conductivity has to go from -0.5 to +0.5. So in fact, if I take the surface and think about what the Hall conductivity is, this says that the Hall conductivity should be integer quantized, but in half-integer units. Okay, and so at first thought, this sort of violates all of the rules that you should think, because the integer quantum Hall effect. I gave you Laughlin's argument, which said that the integer quantum Hall effect has to be integer quantized. Okay, and so this looks like but this is non-interacting electrons, and so it looks like how can you get a fractional integer quantum Hall effect? Okay, so the resolution of this paradox is that the surface, so if I imagine a slab. Okay, the resolution is that the top surface of the slab is always connected to the bottom surface. Okay, there's a theorem that says that if you have, the surface is the boundary of the interior, and there's a theorem that says that you can't cut the surface. Okay, so the surface, the top surface, is always connected to the bottom surface, and so in an experiment, you're always going to be measuring the top surface and the bottom surface in parallel. Which basically doubles this half integer into an integer. Okay, and so in fact, if you had the top and the bottom surface were both in sigma xy equals +0.5, then the reason that the integer quantum Hall effect always has to be integer quantized is because the transport is always in edge states, right? And the edge states always carry an integer conductance. Okay, so what you see here, though, is that the top surface and the bottom surface will share a single chiral edge state that goes around the edge. Okay, and so that's how this fractional integer quantum Hall effect is not breaking the rules. Yes.
So you're saying the 1/2 can never be experimentally observed?
Not in a transport experiment. Okay, because a transport experiment in the quantum Hall effect is always measuring edge states. So look, you can observe it if what you want to say is, you know, I know it's the top and the bottom surface, so I'm going to divide the conductance that I have by 2. Okay, you could do that, and I don't know if you want to claim that's observing the 1/2 or not, but yeah. Okay, yeah, yes.
I think I'm a little confused. Are we in 2 plus 1 dimension, or?
Pardon me?
Are we in 2 plus 1 dimension, sir? It's 2 spatial dimensions.
Well, no, actually, well, the important thing is that we're really in 3 dimensions. Okay, but the surface of the 3-dimensional object is two dimensions. Okay, so these Dirac fermions are 2 plus 1 dimensional. Okay, but they are living on the boundary of a 3 plus 1 dimensional system.
Right, but in the Laughlin argument, that was 2.
In the what?
The Laughlin argument.
The Laughlin argument was 2. Yeah, that's right.
That's for the edge.
Yeah.
Okay.
Yeah. All right. Right. You see, the thing is that the surface can't have an edge. Right? There's a theorem that says that the boundary of a boundary is nothing. Okay? So if you have a surface, the surface can't have an edge. Okay? So all you can do is have connect the top surface to the bottom surface, then you can have a boundary between them, but that doubles it. Okay. All right. So another way of thinking about this is you can sort of imagine taking, another way of, you can break time reversal symmetry with an orbital magnetic field, which gives you Landau levels. Another way that you can break time reversal symmetry is by applying a Zeeman magnetic field, a magnetic field that couples to the spin and not the orbital, okay? And so that doesn't give you Landau levels, but it breaks time reversal symmetry and opens up an energy gap at the surface, okay? And in fact, this is a very nice route to sort of engineering this integer quantum Hall effect in a system. So there are beautiful experiments. I don't have any slides about them, but there are beautiful recent experiments where people have basically taken a topological insulator and put magnetic atoms in it to make it magnetic. And when it's magnetic, then the magnetization basically gaps the surface state and gives you an integer quantum Hall state. And this gives you what's called the anomalous quantum Hall, the quantum anomalous Hall effect, which basically gives you a quantum Hall effect when you don't have an externally applied magnetic field. So in a sense, this is like a realization of Haldane's vision of having a quantum Hall effect without Landau levels. Okay, but in any case, so you could do this. Now, another way you could think about this is you could sort of unfold it. Okay, so I have I've gapped my surface states on the top and the bottom. If I unfold it, then what that is like is having sort of opposite magnetizations. Like this, and then what you learn is that if you have, and so this gives you, putting on the Zeeman field gives you a mass to your Dirac, 2 plus 1 dimensional Dirac fermions, and on a domain wall where that mass changes sign, then again you have one of these chiral Dirac fermion modes. Okay, and so this is sort of an interesting thing that one it would be nice to be able to make something like this. Okay. Yes?
So this chiral mode, is it spatially separated to 2, or is it really just one mode? It's spatially separated into like 2 halves, which can be very far apart.
Well, let's be careful. So you have to. So now, of course, in this picture, I haven't specified what's happening on the on all of the other surfaces of the TI. Okay, so if there's really nothing there, then everything is gapless along the bottom, And then, you know, this chiral mode just sort of goes from this gapless region into the other gapless region. And it's the only chiral mode there is, aside from this. But maybe it would be better to think, imagine you have a sphere of topological insulator, and in the northern hemisphere, I have, the magnetization up, and in the southern hemisphere, I have it down. So then on the equator, there's going to be a single chiral mode that goes around. Okay, and that's all there is. Good. Okay. All right. So another way that you can think about this. Okay, so we have this this kind of fractional integer quantum Hall effect. But it's really it's really coming because we have the two-dimensional surface of a three-dimensional bulk. Okay, and so another way that you could think about this, and this is sort of an insight from Chi, Hughes, and Zhang and others, is that you can think of this as sort of a three-dimensional property of the topological insulator. And the idea is that it's like a magnetoelectric effect. So what I want you to imagine is a cylinder of topological insulator. And let me imagine that around the circumference of the cylinder, I have I've put a magnetization which opens an energy gap. Okay, so it has a Hall conductivity of E squared over 2h, plus E squared over 2h plus some integer which depends on exactly where the Fermi energy is. Okay, so the point, though, is that if I apply an electric field down the cylinder, so then let's think about what happens. So an electric field down the cylinder, so that's going to give me since there's a Hall conductivity on the circumference, that's going to give me an electric current which flows around the surface of the cylinder. Okay, and if you think about, just go back to freshman E&M, it's like a solenoid, right? And so that current going around is going to create a magnetic field down the axis. Okay, and so you can compute it, and so that is like a magnetization that gets produced in the system. Okay, so if I think of this this current going around as being like a bound current in a bar magnet. Okay, that is just like a magnetization. And so what you learn is that you get a magnetization which is proportional to the applied electric field. Okay, and so this is called a magnetoelectric effect. And the coefficient of this magnetization is related to this this quantized Hall conductivity. Okay, and now of course the quantized Hall conductivity, it's only the fractional part of it that's quantized. You could always add an arbitrary integer multiple of E squared over h, and that's sort of so this integer is not determined by just what's happening in the bulk. But the 1/2 is. I could change the integer just by putting in a two-dimensional surface of quantum Hall effect on it. Okay. So what this means, though, is so I can interpret this magnetoelectric coefficient if I want to think about a Lagrangian that would give me a magnetization proportional to the electric field, then it would be a term which is E dot B. Okay, and so having a term in a Lagrangian proportional to E dot B, that's sort of a famous thing. So this is often called a theta term, and so what this suggests is that this 1/2 tells you that the theta is equal to pi modulo 2 pi. And so you can sort of think that now time reversal symmetry, if you had it, would say that take theta to minus theta. Okay, but since theta is ambiguous modulo 2 pi, then having a theta term equal to pi is consistent with time reversal symmetry. Okay, and so this is this idea that in a topological insulator you have a theta equals pi. Okay, so in a sense, this this is kind of like the story that I told you about the electric polarization in one dimension. So remember, in one dimension we had this this quantity which is the electric polarization, and it was uncertain because I could always add an electron to the end. Okay, so the fractional part of the electric polarization was meaningful, but it was only defined modulo E. And likewise, the Berry phase, going around the Brillouin zone, the fractional part of that was all well defined, but if I do a large gauge transformation, I can change it by an integer. So these two sort of have the same ambiguity. So the story is the same for this theta term. So if I think about the magnetoelectric polarizability, then the part that is determined by the bulk is only the fractional part of this. It's this 1/2. I could always add, just by adding an extra quantum Hall layer on the surface, I could change this by E squared over H. And now it turns out it's possible to determine what this theta term is in terms of the block band structure, and I'm not going to explain how to derive this formula, but what this formula is it's sort of a three-dimensional generalization of this, and so this is called a Chern-Simons form, and so this is a quantity which again is gauge invariant under small gauge transformations, but if you do a large gauge transformation, this can change by an integer. And so it has the same property that that it has this intrinsic ambiguity. It's only the fractional part of it that is meaningful. Yes.
Do you need the trace there?
Do I need the trace? Yeah. So I'm viewing this A now as a matrix. So if I have block states, then I have, A is UI d by dk uj. So it's a matrix.
You're talking about degenerate.
Huh?
Degenerate ground state, since it's a matrix.
No. I have many bands. Okay. Yeah. And so in general, so I have to use the fact that this connection is actually not a U1 connection. It's actually, there are more states.
No,
Yeah.
the Berry connection is typically defined with respect to a single eigenstate or an eigensubspace. So what do you?
Well, now I have several of them. So I have several bands now. So I have a UN. I have several bands, and I can imagine rotating by a UN transformation among those bands. That doesn't, if I have n occupied bands, if I do a UN transformation among those bands, that doesn't change the many-body ground state.
I see. So you're only considering not necessarily all the states, but a finite number of such states.
Yes.
You're looking at the connection.
Yeah, the finite number of say, occupied states.
Okay.
Yeah.
Because if you considered all of them, it would be a trivial connection.
I agree, but I'm only considering the occupied ones. Yeah. Okay. All right. Okay. So so when you break time reversal symmetry on the surface, we're still doing non-interacting electrons. So in the case it's trivial, but it's there's some interesting subtleties associated with that. So now what I want to talk about is I'm going to stop talking about topological insulators for a little bit, and I want to introduce the idea of topological superconductivity. And in order to introduce topological superconductivity, let me just say a few words about superconductivity. Okay, and so so here I think we have we have different backgrounds that you have. And so for the condensed matter theorists, we learn about semiconductors first, and then we learn about superconductors, and then we learn about Majorana fermions. Okay, and so for me, I was able to understand a superconductor by thinking of it as being like an insulator. And then that allowed me to finally understand what Majorana fermions are about. Okay? Whereas for those of you with a high energy background, the first thing you learn about is Majorana fermions, and then maybe you learn about superconductors, and then maybe you learn about semiconductors. And then you say, well, I finally understand what a superconductor is because it's just Majorana fermions. So I'm going to give you my perspective on this, which is to think about a superconductivity. So what you do in a superconductor, so basically the magic is that in mean field theory, the mean field description of a superconductor is a theory of non-interacting fermions. Okay, but the price that you pay is that so when you do this mean field theory is that you have so your Hamiltonian is quadratic in the fermion operator, so it's a free fermion theory, but it has these anomalous terms which with two creation operators or two annihilation operators. Okay, and so in order to describe this, then what one usually does is to write the Hamiltonian, write the many-body Hamiltonian as a matrix like this, where both on the left and on the right I have both psi and psi dagger. Okay? And so now, so then when I do that, I can write a Hamiltonian that involves these anomalous terms, and the anomalous terms sort of give me the off-diagonal components of this matrix. Okay? Now, when I've done this, though, I've done something drastic because I've made two copies of my original problem. Okay? And so, so by making these two copies of the original problem, what I'm able to do is I'm able to turn this sort of non-trivial superconducting problem into a problem that looks like an insulator. Okay? So again, so now I have this Hamiltonian, and in a superconductor there's an energy gap. Okay, which, it has a conduction band and a valence band, just like an ordinary, band structure that I've been talking about all along. But the price that I paid is I made this artificial doubling. And so by making this artificial doubling, I have introduced an intrinsic symmetry that this Hamiltonian has to obey. And so it has to obey sort of an intrinsic particle hole symmetry. So remember when I talked about the Sushri-Verheugen model, I said there was some artificial symmetry that it has that guarantees that the conduction band is a mirror image of the valence band. So this now is a real intrinsic symmetry, and in fact, it's a symmetry actually that kind of looks like time reversal symmetry. So my Hamiltonian anti-commutes with this operator, but this operator is an anti-unitary operator, which sort of is like time reversal symmetry. Okay, and so this Bogolubov-de Gennes Hamiltonian is like the Hamiltonian of a insulator, if you will, but it has this intrinsic symmetry. And moreover, in addition to having this intrinsic symmetry, again, the conduction band looks just like the valence band, but in fact, the conduction band and the valence band are redundant with each other. Okay, which means that I can consider two different, in an insulator, I can consider two different excitations. I can imagine adding an electron into the conduction band, or I can imagine removing an electron from the valence band. Okay, and in an insulator, those are two different states. Okay, in fact, they have different numbers of particles. Okay, but in a superconductor, these are actually the same state, and the reason so the reason they look different is because we introduced this artificial doubling. Okay, and so one has to keep in mind and the reason these can be the same, of course, is because you can give Cooper pairs away to the condensate for free. Okay, and so the number of Cooper pairs is not definite in a superconductor, and so that's how these two can be actually the same state. Okay, and so so we have to keep this redundancy in mind, that adding a particle into the conduction band is the same thing as removing a particle from the valence band. Now, so now we can so now that we've turned this problem of superconductivity into a problem that looks like an insulator, then that poses the natural question: could there be topological classes of superconductors? Okay, and so now, though, what we have is we have to impose a different symmetry. So remember, when we imposed time reversal symmetry, we got some extra topological structure, which was different than what we had when we didn't have time reversal symmetry. So now we have to think about what happens if we impose this this intrinsic particle hole symmetry. Can that give us any different topological classes? Okay, and so the answer, of course, is yes. You can have topological superconductors, and the simplest version of this is thinking about one dimension. Okay, and so in order to sort of understand this in the most simple way, what I want to do is I want to do what I've been doing all along, which is to first think about the boundary and ask, well, what kinds of protected things can I have on the boundary? So the boundary of a one-dimensional system is, of course, the zero-dimensional end. Okay, and so if I have a superconductor with an energy gap, then it's always possible that I could have states which are, inside the energy gap, and these states are then localized. They're sort of exponentially localized at the end. Okay, and so depending on what the Hamiltonian at the end is, you might have these end states. But the thing is that because of this intrinsic particle hole symmetry, is that if you have a state at energy E, then it has to have a partner at energy minus E. Okay, unless you had a state that was at exactly zero energy. Okay, and so this zero energy state would be its own partner. Okay, this doesn't break the rules. This still has the particle hole symmetry. But what you can tell is that if you have this state exactly at zero, then you can't get rid of it, because if you tried to move it away from zero, then its partner would have to appear out of nowhere. Okay, and so that can't happen continuously, and so this zero mode is topologically protected, in the same way that the chiral edge state of the integer quantum Hall effect is topologically protected. You can't get rid of it by doing a smooth deformation. The only way you could get rid of it is by making this bulk gap close down to zero, and then you could get rid of it. Okay, and so now, of course, what is it that determines whether or not you have this zero mode at the end? Well, it's whether or not the one-dimensional superconductor is a topological superconductor or not. Okay, so now, of course, this zero mode is sort of a magical thing, because I told you that we have this intrinsic redundancy that we've imposed in our states, and so adding a particle at energy E is the same thing as removing a particle at energy minus E. Well, that means that adding a particle at energy zero is the same thing as removing a particle at energy zero. So that means that that adding a particle into this state does exactly the same thing as removing a particle, so it's like the particle is its own antiparticle. Okay, and so this is the defining feature of a Majorana fermion. And as Shivaji explained yesterday, we can think about this Majorana fermion as being like the real part of an ordinary Dirac fermion, which can either be occupied or empty. Okay, and so two of these Majorana modes defines a single Dirac fermion. Okay, and so for instance, if you have a one-dimensional topological superconductor, you're going to have a zero mode at both ends, and those zero modes define a single Dirac fermion, which defines two states. Okay, and so this is a interesting situation where of course, if your one-dimensional system is very, very, very long, if it's effectively infinitely long, then this zero mode is protected. If it's finite, then the zero modes that you have at each end will couple to each other, okay, just like in what Shivaji was describing yesterday, and so they will split a little bit, and so you'll have a two-level system like this. Okay. All right. So good. So this is the sort of one-dimensional topological superconductor. Okay. So Shivaji introduced this Kitaev model yesterday, and so what I thought I would do is sort of show it to you again, sort of from the perspective of the way I was describing topological band structures before. Okay, and so Kitaev introduced this very simple and beautiful model of a one-dimensional P-wave superconductor, which you can basically think of as a chain of a one-dimensional chain of sites which have a hopping term on it, and then and there's a chemical potential term which sets where the Fermi energy is, and then there is a pairing term which adds a Cooper pair to a neighboring pair of sites. Okay, and so this is spinless electrons on a one-dimensional lattice, and since the electrons are fermions, this pairing term is necessarily a p-wave a pairing term. Okay, and so given this Hamiltonian,
Since there's no conserved quantity, what is n?
What is
You have h minus mu n on the left.
h minus mu
First
n?
line on the left.
Yeah,
You've written h minus mu n.
it's this.
Oh, okay. So even though it's not a conserved quantity for that Hamiltonian.
Right, but it's n. Yeah. So C dagger C is that's an operator. I mean that's n. Yeah. So right. So this Hamiltonian, okay, I can write as a matrix like this, and if I do it as a function of k, then I have a Hamiltonian which is just like the Hamiltonian for an insulator, a one-dimensional insulator, okay, and it's a 2x2 matrix. Okay, and so this 2x2 matrix, the sort of non-superconducting part of it is on the diagonal, and it's just the one-dimensional tight binding model with a chemical potential, and then multiplied by tau z, which is h and minus h on the diagonal. Okay, and then the off-diagonal term is going to be this superconducting term, which gives you a sine k. Okay, and so I can think of this as so this looks just like so since it's a 2x2 matrix, I can do the same game that I had before, which is that I can think of it as a vector dotted into the Pauli matrix. Okay, and then and so you can see that this this d vector lives in the xz plane. Okay, and so it looks kind of like what we had before. Okay, in the Schrieffer-Heeger model. So there are two phases. So if mu is very large, then dz never gets to zero, and so it's sort of a trivial phase, if you will. If dz is very small. If mu is very small, then you can see this d vector wraps all the way around. Okay, so in fact, these two phases are the trivial and topological phases of this one-dimensional superconductor. So this model is almost the same as this Schrieffer-Heeger model. It's a little bit different in the sense that so in the Schrieffer-Heeger model we had this symmetry where the Hamiltonian anti-commutes with sigma z. Okay, so this one we have the symmetry is different. It's this anti-unitary particle hole symmetry, and the constraint that gives you on this d vector is a little bit. It relates d and minus d. Okay. Okay, and this fact again guarantees that this Berry phase going around is either 0 or pi. Okay, and so there really are two different topological phases that you can have. Okay, so this is a way of thinking about the of this one-dimensional Kitaev model. Now, of course, Kitaev was able to make this model even simpler. Okay, and by thinking of each of these sites as a so each of these sites has an operator C on it, which is a Dirac fermion, and so Kitaev imagined thinking of this as a pair of Majorana fermions. And so again, as Shivaji explained, then if I think of each site as a pair of Majorana fermions, then the chemical potential term sort of gives me a term which couples the Majoranas on a single site, whereas the combination of the superconducting term and the hopping term give me something which connects different sites. And so the important thing is that there's a particular ratio between the superconducting term and the hopping term, which makes this Majorana problem just a nearest neighbor Majorana chain. Okay, where you just have the coupling between these Majoranas, and you have the coupling between these. Okay, and so that means when delta is equal to t, then we have this simple Kitaev chain where it's clear that when T1 is bigger than T2, then you don't have anything at the ends. But when T1 is less than T2, then you have these unpaired Majorana modes that live at the end. Okay. So so this is the Kitaev's Majorana chain. Yes.
So the fact that your D vector lies in that plane, is that a gauge dependent state?
Yes. So if I do a U1 gauge transformation, so what that does is that changes the phases of these C's. Okay, and so what that effectively does in this Hamiltonian is it rotates the D vector about the Z axis. Okay, so if I change the phase, then instead of being tau x here, it'll be some tau that's living in the xy plane. Okay, so yes, it is a gauge dependent property. Yeah. Okay. Okay, so this is a one-dimensional topological superconductor. You can ask, well, what about higher dimensions? Can there be topological superconductors in 2 dimensions or 3 dimensions? So in 2 dimensions, again, we can think about the boundary. And you can ask yourself, well, let's suppose I have the boundary of a 2-dimensional superconductor. Could I have any kind of modes that could be protected? Well, so for the ordinary 2-dimensional insulator, I could have a boundary which was a 1-dimensional chiral Dirac fermion. Okay, and those you can't get rid of. Okay, and so we know that there have to be topological states which give us the Chern number. Okay, so here in a superconductor you could have the analog of that, which is a chiral Majorana fermion mode, and so this is just like a chiral Dirac fermion mode, except there's a redundancy between the states at positive energy and the states at negative energy. Okay, and so this is sort of like half of a chiral Dirac fermion. Okay, in the sense that if I had a pair of these, I could think of them as being the real and imaginary parts of a chiral Dirac fermion. Oh. Pardon me? Yeah, so this will happen if I have a non-zero Chern number in the Bogolubov-de Gennes Hamiltonian. Okay, so because you see, this is just, once I turn the problem into the Bogoliubov-de Gennes Hamiltonian, where I have this intrinsic, redundancy, then this is just the Chern number problem. It's the same problem that we had when we had the quantum Hall effect. So in fact, so there's a simple model that you can write down for this, which is so the Reed-Green model, which is a so again, it's just like the Kitaev model that I wrote down, where so I have just a parabolic band with a chemical potential, okay? And then I have a pairing term, and so what I want to have is I want to open up a gap everywhere on the Fermi surface, but since it's spinless electrons, it has to be p wave, and so what I'm forced to do is to have a delta which is like p plus ip. Okay, so the phase of this superconducting term sort of advances when I go around the Fermi circle. And so if I do that, then what you can see is, so I can translate this now. So this is sort of, a sort of continuum version of it. I can also write a lattice version of it on a lattice that again has this sort of structure, okay? And if I do that, then again, when mu is very large, this d vector does not wrap around the origin, okay? And so remember, I told you that in a two-level Hamiltonian, which is a function of two variables, the Chern number is the number of times that the d vector wraps around the sphere. Okay, and so here clearly it doesn't wrap around the sphere, whereas in the weak pairing phase, when mu is close to zero, then it does wrap around the sphere. Okay, and so the Chern number of this Bogoliubov-de Gennes Hamiltonian is 1 in this case. And then, so then that the edge states in the Bogoliubov-de Gennes Hamiltonian have to have these chiral modes, okay? But since it's a Bogoliubov-de Gennes Hamiltonian, we have this intrinsic ambiguity between intrinsic redundancy between the plus states and the minus states, so it's really only half of a chiral Dirac mode. It's a chiral Majorana mode. Okay? Yes?
You've fixed a couple of places determining about U and T here. Is there any dependence on delta?
I'm sorry, say that again. So does it depend on? Yeah, I think maybe I'm saying when T is equal to delta, this is the case. Yeah, I think that's right. Yeah. Yeah, I think it should be. So the boundary probably does depend on delta. I think maybe I assumed that T is equal to delta when I wrote this. Yeah. Yeah.
The 1D case, you have these two pictures where one of them had no zero mode and one of them had a zero mode. So, what is the significance of having two zero modes? Right? Why is that not a class of its own?
Okay, good question. So here it's clear that you could have two chiral modes. Okay, so if I had two chiral modes, then you can't get rid of them. Okay, whereas if I had two zero modes, then there's nothing to prevent me from adding a term that splits them. Okay, and so from that fact, what you can deduce is that there can only be two classes of one-dimensional topological superconductors, but there's a whole integer family of topological classes of two-dimensional superconductors. So the topological classification for superconductors is different in 1 and 2 dimensions. Okay, and in fact, that leads me to you can ask the question, well, what about 3 dimensions or 4 dimensions or 8 dimensions? And so this leads to a general problem of how do you classify topological band structures with all different kinds of symmetries in all different kinds of dimensions. Okay, and so that's so I'm going to get to that, but let me say one more. Let me say one more thing about the two-dimensional topological superconductor, which is okay. So we know that we have these chiral modes. Okay, so an interesting thing then is to ask what happens if you drill a hole in your superconductor and thread a flux, or what if you have a vortex in your superconductor. And so this is a important problem, which is that if you have a two-dimensional topological superconductor and you put a hole in it, then you know, around the boundary of the hole there's going to be a chiral Majorana fermion mode. Okay? But of course, since the hole has a finite circumference, the momenta of these chiral modes is going to be discrete. Okay, and so then you know exactly which momenta you pick out depends on the boundary condition for how the Majorana mode, how the phase of the Majorana mode changes when you go around. So when the Majorana mode goes around the circle and there's no magnetic field, then it's rotating by 2 pi, so it picks up the minus sign for a fermion. And so what that means is that when there's no magnetic field, then you get a set of discrete states, but they miss 0. Okay? But when you apply a magnetic flux in here, then that changes the boundary condition. Now, of course, in a superconductor, you're not free to choose just any magnetic flux. You have to choose a multiple of the superconducting flux quantum, which is h over 2e. Okay? And so if you have a h over 2e vortex, then a fermion going around that h over 2e vortex picks up an additional minus sign. Okay, and which cancels the other minus sign, so that you can have a state exactly at 0. Okay, and so the upshot of this is that when you have an odd number of flux quanta piercing this hole, you have a discrete 0 energy state on this vortex. Okay, and so a vortex in a two-dimensional topological superconductor binds a Majorana 0 mode. That is one of these discrete Majorana 0 modes. Okay, so of course you don't have to drill the hole in the superconductor. So if you have a type 2 superconductor which supports vortices, then this can sort of happen by itself. And so there's a classic theory from back in the 1960s that shows that if you have one of those vortices, then actually you have lots of these, these states in a ordinary superconductor are going to be pretty finely spaced. So this level spacing is like the superconducting gap squared divided by the Fermi energy. Okay, and so in general, if you have a superconductor where the Fermi energy is big, much bigger than delta, then these states are going to be very finely spaced. So what you'd really like to do is you'd like to make this Fermi energy as small as possible. So maybe if you could tune the Fermi energy to a Dirac point, then maybe this level spacing would not be so small. Okay. All right. So this is a vortex in a topological superconductor. So now let me just say a word about this sort of general topological classification problem. So I told you, so we have so basically if we're talking about classifying free fermion problems. So we can have time reversal symmetry. Okay, so time reversal symmetry again is an anti-unitary operator, which so it takes k to minus k, and it squares to. So if you have spinless electrons, it squares to +1, but electrons really have spin, so it really squares to -1. And you can also have particle hole symmetry, which anticommutes and squares to plus or minus 1. Or you can have the unitary chiral symmetry, like we had in the Schrieffer-Heeger model, which you can sort of think of as like the product of these two. And that's a unitary operator that anticommutes with the Hamiltonian. So given these combinations of symmetries, then there are various possibilities that one can have. And these, in fact, are the 10 Altland-Zernbauer symmetry classes for random matrices. Okay, and so this is something which I think. So I'm not going to go into any mathematical detail here, though I promise you that next week you'll get as much mathematical detail as you want. So Greg Moore will talk about this, and this is something that he understands much better than I do. So what I understand is the sort of special cases, okay, and so in particular, class A, where you don't have any of these symmetries, that describes the quantum Hall effect. So you have a quantum Hall effect in 2 dimensions. In general, there will be a quantum, and this is characterized by the Chern number. In 4 dimensions, there's another kind of quantum Hall effect you can have, which is characterized by the second Chern number, etc. Class A2 is the class where you have just time reversal symmetry squaring to minus 1. So that's the class when you have spin-orbit interaction in an insulator. And so in 2 dimensions, you have a Z2 topological insulator. In 3 dimensions, you have a Z2 topological insulator. In 4 dimensions, you have an integer class of topological insulators. So these are characterized by, again, a second Chern number, which you can have, which is sort of consistent with time reversal symmetry in this class. Okay, so the topological superconductors I was talking about. So again, we realized that in 1 dimension it's a Z2. There are 2 possibilities, whether you have a 0 mode or not. But in 2 dimensions, there's an integer class of these. Depending on you can have any integer number of chiral-Majorana edge modes. So it's got to be an integer. Okay? And so then there are more symmetry classes. You can imagine a superconductor with time reversal symmetry. And so this is an important class. So this is class D3. So in 1, 2, and 3 dimensions, you can have time reversal invariant topological superconductors. Okay? And then there are other symmetry classes as well, and there are various situations in which those could be important as well. Yes? I'm sorry, speak louder.
If the chiral symmetry was proportional to the product of the other 2 symmetries, why is the number associated to it not like minus 1? Rather, why is it 1 when like minus 1 times 1 is minus 1?
Well, no. So this minus 1 is what theta squares to. Theta squared is minus 1. And pi squared is minus 1. So this 0 and 1, I'm just saying whether or not I have this symmetry or not. That's all I mean. Yeah. Yeah. Yes.
So this Majorana 0 mode is general. You have a superconductor and you have a vortex.
If you have a topological superconductor and you have a vortex. You see, it's important, again, so let's imagine we had a trivial superconductor. I drill a hole in it, then it doesn't have this chiral-Majorana mode on it. Okay, so there doesn't have to be anything. Now, in general, if you again have delta much less than EF, what you'll find is you'll find that there are going to be bound states inside the vortex, but they're going to miss 0. Yeah.
This may be naive, but when does particle square to minus 1 physically?
Okay. So let me first talk about time reversal. Okay, so when could time reversal square to +1 physically? Okay, because you see, really, I told you know the -1 that you get is really the phase that you get when you rotate a spin by 2 pi, and that's the real answer. Okay, how could you get +1 if you do not have spin-orbit interaction? So if you have a situation where the spin-orbit interaction is very weak, so that we can turn it off, and that happens if you have materials that are made out of light atoms where the electrons never go fast enough to experience the relativistic effects that give you the spin-orbit interaction. So if that's the case, if you can ignore the spin-orbit interaction, then then effectively you have a symmetry which is under rotation. You can independently rotate spin. And so then you can combine this spin rotation with the real time reversal operator to give you a time reversal symmetry which is just complex conjugation. It doesn't rotate the spin. And that squares to +1. Okay, so if you have this extra symmetry, which is spin rotational symmetry, then you can have time reversal squaring to +1. And so it's the same story with the particle hole symmetry, I think. So the intrinsic particle hole symmetry squares to +1, but if you have spin rotational symmetry, then you can have it square to -1. Okay, all right. Okay, so for topological superconductors, we have this I want to say a little bit more about these Majorana zero modes these discrete Majorana zero modes. There's something, of course, we very much would like to make come to life in the real world, the reason for that is this brilliant insight that Alexei Kitaev had, which is that the degenerate states that you have due to a pair of these discrete Majorana zero modes can give you a method for storing and manipulating quantum information. Okay, and so again, the idea is that two of these separated Majorana bound states defines a single Dirac fermion, if you will, which has two states. It can either be occupied or empty. Okay, and
when you do the BDG transformation, it seems that the chiral symmetry is always there automatically.
No. The symmetry that's always there when you do BDG is the anti-unitary. It's the particle. It's this one. So in general, if you don't have time reversal symmetry, then you don't have to have the chiral symmetry in a topological superconductor. So in D3 you do have the chiral symmetry, but in class D, which is a superconductor without time reversal symmetry, then
so in BDG you always have the particle hole symmetry, right? Once you do the BDG rewriting of the Hamiltonian, right?
yeah. So the Hamiltonian at K is then related to the Hamiltonian at minus K by the particle hole symmetry. Right. So the point is that the intrinsic symmetry that you have is a anti-unitary symmetry that involves complex conjugation.
Right. So how is it then that some states cannot have this particle hole symmetry? I mean, it seems to me, maybe I'm missing something, but it seems to me that once you rewrite it as BDG, you always have this thing.
Well, no. So you always have there's always you do have a positive energy state has a partner which is a negative energy state. But there's sort of two ways you can make that happen. You can either make it happen by having a unitary operator that anti-commutes with your Hamiltonian, or you can have an anti-unitary operator that anti-commutes with your Hamiltonian. Okay, and those two are different. Okay, and that's the chiral symmetry is the unitary operator that anti-commutes with the Hamiltonian, whereas the particle hole symmetry is the anti-unitary operator. So and those are two different cases.
I was a little anxious. Just what is this the K theory of?
Ask Greg. Ask Greg. Yeah. So yeah, or ask maybe Professor Witten will be able to explain that to you. So I only have a very dim understanding of what K-theory is. So I don't want to. I think I would probably say something that's wrong if I tried to answer that. Yeah. I'm sorry. Speak louder. Yeah, that's. Yeah, I think there's a historical. I'm not sure exactly what the history of that name is. So I think it has something to do with the chiral symmetry and the Dirac equation, but I don't have a good answer for that, for why that nomenclature. Yeah. Yes.
How many of the possibilities in this table have been realized?
Well, so certainly, so it depends what you mean by realized. Okay, so there's realized in theory and there's realized in experiment. So let's see. I don't know if I have all these in my head or not, but certainly class A, and so class A1 is if you have something that has very weak spin-orbit interaction. So that I think you can approximately realize, the extent that you can set the spin orbit to 0. And then, so class D, I think we, now of course there's a question as to whether we have realized the non-trivial topological classes of these. Okay, we would like to think that we have, but that's still under debate. Class A2, I think we're in we're under, that's under control. Now there are other ones. So for instance, these ones, you could imagine having superconductors that have spin rotation, that don't have spin orbit. Okay, and so I think there are things that you can do there. So for instance, it may be possible to have these. Now, I don't think there are any experiments. I'm not sure there are experiments that talk about these. So, yeah. So, all right, good. All right. Okay. So let me just say that. So Kitaev's insight was that if you have a bunch of these well-separated Majorana modes, say 2n of them, then that's a way of storing n qubits of quantum information. Okay, and the beauty of this is that if the Majorana modes are well separated from each other, then the quantum information is stored non-locally, which means that if you just look at one of them, okay, then you can't measure the state that that qubit is in. Okay, and so this, and this is the whole problem with trying to make a quantum computer, is to try to keep the quantum computer from accidentally measuring itself. Okay, and so in principle, if you can store the quantum information in these well-separated, Majorana modes, then you can protect the quantum information from sort of local sources of decoherence. Okay, and so that's the dream that we can do that, and then one can do even a little bit more, which is that if you can find ways to sort of braid these zero modes around each other, then you can manipulate the states that you have. Okay, and that's sort of, so you can do a unitary operation on these qubits that you have. Okay, and that's sort of what you'd want a quantum computer to do. You want to have it store information, then you want it to perform unitary operations on this. Now, unfortunately, with these Majoranas are a little bit too simple. So even if you could make these work, the operations that you can do are not powerful enough to make a universal quantum computer. Okay, but I think they'd be a good start. So we very much like to make these happen. Okay. Yes.
Can you explain how the metric gradient changes state?
How do I get from this to this? Yeah, so it's basically contained in this rule. So the idea is that if you exchange two Majoranas, then one of them goes to the other, but the other one goes to a minus sign. And the reason you have that minus sign is because if you think, the Majorana is like a vortex, so a fermion going around that vortex picks up a minus sign. Okay, so I can think of a vortex as being connected to a string around which the fermion picks up a minus sign. And so if I do an interchange between them, I think you can convince yourself that one of them is going to cross the string and not the other. Okay, and so that's the origin of this minus sign. And so there's a little bit of, you have to go through a little bit of algebra to see that this interchange rule sort of gives you this transformation. I don't think I can't do that on the top of my head right now, but it follows from this. Okay.
So, what are the sources of local incoherence?
Interaction with other degrees of freedom.
And they're always local.
Well, so we like to think that that physics is local. Okay, but of course, there's local and there's really local. Now how these things are local to the extent that they're the wave functions of these modes we think decays exponentially. Okay, now e to the minus 10 isn't that small, right? So I think there's a practical concern of how local does local have to be in order to make this work, okay? And so I think that's a practical question. If anything like this is ever going to work, that practical question is going to have to be addressed, head on. Okay, but what we can say is that exponentials get really small when you make them really far apart, and if you're able to separate them by a really long way, then the exponential is going to save you. But so the practical question is in a realistic setting, they're not going to be miles apart, right? So how good is good enough? And that I think is a practical question that needs to be addressed. Yeah.
Question in the last sense: is there an easy way to see that? Does that have to do with some irrational number?
Yeah, it basically has to do with the fact that these kinds of operations. So you think of, when you do operation on a qubit, you can think of doing a rotation on the block sphere. So the state of a qubit you can think of is like a spin. It's a vector on the block sphere. So these kinds of rotations, they only allow you to do rotations by 90 degrees. Okay, and so you can't get everywhere by just doing 90-degree rotations.
Is it obvious that the only rotations non-abelian braiding allows you to do are 90-degree rotations?
Well, it's because of these. It's because of this rule. This is all you can do. Yeah. All right. Okay, let's see. So I have 15 minutes. Is that right? Okay, good. All right. So, okay. So look. So this is something we very much would like to make happen, and this is something people are trying. So how can you make these Majorana fermions come to life? So actually, originally, there's proposal by Moore and Reed. And the idea that this could arise in the fractional quantum Hall effect. Okay, and so this is really where some of these ideas, were first thought about. And so there are experiments in the nu equals 5 halves fractional quantum Hall effect, which sort of look like what you'd want to make happen, and so it might be that this is indeed a venue for these Majorana fermions. But in terms of these superconducting topological superconductors, so one thing one can do is one can try to, one of the problems is we're not given topological superconductors. Okay, so there are various proposals for how one might be able to find unconventional superconductors that have topological superconductivity, and this is something which I think is not we don't have definitive examples of those. So another idea, though, is that, what if we just use an ordinary superconductor, but we combine it with some other kind of material that has some topological properties? Okay, and so they're using, and we can induce superconductivity in that other material using the proximity effect. And so here there's been a fair amount of effort. So there's an idea that you can, if you can make the surface of a topological topological insulator superconducting, then you get something like topological superconductivity. And then there's ideas that one can, you don't even really need a topological insulator. You can do it with semiconductors and in particular quantum wires or ferromagnetic atomic chains. And it's these ones which have had a lot of promising experimental developments. And so I'm just going to say a few words about those. So the idea, so Zahid mentioned this a little bit yesterday, but let me just say that there's something special about the surface of a topological insulator. So remember, let me remind you, the thing that's special about a P plus IP superconductor, so remember a P plus IP superconductor was this a two-dimensional topological superconductor which has the Majorana modes at a vortex. And so the thing that's special about that is that you have a Fermi surface, but you have spinless electrons. So there's just a single state for electrons going around the Fermi surface, and then I'm pairing the states at k and minus k. Okay, and I'm pairing them with a P plus IP type order parameter, and that gives me this topological superconducting state. Now, an ordinary superconductor is different from this, though, because an ordinary superconductor has spins up and down, which are paired into a singlet. Okay, and so an ordinary metal has two Fermi surfaces, one for the up spins and one for the down spins, and they're sort of paired to each other in a singlet, and that gives you, that's sort of like two copies of this, if you will, and that is not a topological superconductor. Okay, but if you look at the surface of a topological insulator, if you are able to make it superconducting, so now you can make it superconducting. You're pairing. So the surface of a topological superconductor is only half of this, but it has the up spins and the down spins on opposite sides, and so you can do a singlet pairing of these, but you still only have half. And so this is sort of like this, okay? And in fact, it supports these Majorana zero modes at vortices, okay? And so the idea then is that by using this surface of a topological insulator, if you have an H over 2E vortex, in fact, you have this Majorana zero mode bound at this vortex. Okay, and there are other ways you can do this too. If you instead take the two-dimensional quantum spin Hall insulator, okay, then you have the helical edge state of this of the quantum spin Hall insulator, and you can gap that with a superconductor, or you can gap it with a magnetic gap. And on the boundary between these two, then there will be a Majorana zero mode. Okay? And so this is sort of like the one-dimensional topological superconductor. Okay? There's a difference, though, which is in the one-dimensional topological superconductor, you actually have to break time reversal symmetry, okay, in order to get the Majorana mode. And the superconductor itself breaks time reversal. Here, the superconducting state doesn't break time reversal, but it's the insulator on the outside that does break time reversal. Okay, and so this is sort of a complementary situation to the one-dimensional topological superconductor. Okay, so there are other things you can do. So you can make so if I look at the surface of a three-dimensional topological superconductor on an interface between a superconducting gap and a magnetic gap, then there will be a one-dimensional channel, which again carries a which is sort of like the edge of a two-dimensional P plus IP superconductor, and so this has a chiral Majorana mode. Or you can have a sort of a Josephson junction between superconductors, and then when the phase difference is equal to pi on this Josephson junction, then you have sort of a non-chiral Majorana mode when the phase difference is equal to pi. So there's different sort of ways that you can introduce these sort of topological superconductivity in these topological insulator type structures. Okay. Now, so an important insight. So this this idea, I think that you could do it with a topological insulator. That was sort of the first idea that you can use a proximity effect. But shortly afterwards, it was realized that you don't really need the topological insulator. What you really need is you need to have this sort of half of an electron gas. And so if you have an ordinary semiconducting material that has a strong spin orbit, then what it can do is it can give you sort of this Rashba type band structure. Okay, so if you have a Rashba term, then what it does is it spin splits the energy bands in a way where you have a Kramer's degeneracy at k equals 0, but then it gets split like this. And so the idea then is that if you break time reversal by either applying a magnetic field or by having some magnetic interaction, then what you can do is you can open a gap at this Kramer's degeneracy point, and then if you can put your Fermi energy inside that gap, then you just have a single Fermi surface, which sort of looks like the helical Fermi surface. Okay? And then if you make this superconducting, then that's good enough to make it into a topological superconductor. Okay? So somehow, once you have the topological superconducting state, you can break time reversal. Let's suppose you were doing it with a topological insulator. You make it a superconductor, the surface a superconductor, then you can break time reversal symmetry, and you still have this topological superconducting property. Okay, so the time reversal symmetry wasn't essential to begin with, and so you can do it in this case as well. Okay, and so once this idea was out there, then there are lots of different ways that one can go about trying to do that, and so I think Amir is probably going to talk a little bit more about the experiments here. So there are some experiments that Amir is going to tell you about attempting to do something at least on these quantum spin Hall insulators. So they're not at the point where they can see anything that's related to the Majoranas, though they do see something interesting by making these Josephson junctions mediated by the quantum spin Hall insulator. And then in the one-dimensional system, there are two very promising experiments, one done at Delft and one done here at Princeton, where they have observed what you would want to, the first thing you would want to see when you're looking through the Majorana is you'd want to see this, you'd want to be able to tunnel into this zero mode. Okay, and so they see a peak in the tunneling density of states, both in these semiconductor quantum wires and also on these atomic chains of ferromagnetic ions sitting on top of a superconductor. And these peaks are what you would want to see if you were looking for a Majorana zero mode. Of course, the challenge for these experiments is to rule out all of the less interesting explanations for what this zero mode is. But I think this is very, very, very promising and exciting experimental development. But as it stands, these experiments are not taking advantage of the thing that is so interesting about these Majorana zero modes. Okay, and so that's a challenge for the future, is to actually do something with these that takes advantage of this sort of non-local way in which the quantum state is stored. Okay, all right. So let's see. I have 5 more minutes left. I have several different things I could do. I think maybe what I'm going to do is just talk about this one last thing. This is something that's a little bit more recent, and I just want to give you a flavor for what could happen if you have strong interactions. So I told you that if you have a topological insulator surface, then you can open an energy gap on it. If you break time reversal symmetry, you get this magnetic state. If you break gauge symmetry, with the particle conservation, then you can get a superconducting state, which opens a gap. And both of those are kind of interesting. Okay? And so then the question is can you open a gap on the surface without breaking any symmetry? Okay? And so let me try to, so let's suppose you could do that. And what I want to show you is what kinds of properties would that state have to have if you could do it. Okay? And so in order to think about that, I want to give you a couple of arguments, simple arguments, and then there's actually been a whole lot of progress in our understanding of this, though I don't think that this progress is yet in its final form. So there may be room for more ways, for simpler ways of thinking about this. But so what I want to imagine first is doing a kind of Laughlin construction argument. Okay, and so what I want to imagine is I have my topological insulator, and first I'm going to surround it by magnetic material. So I open up a magnetic gap on the surface. Okay, so the entire surface is like it's in this quantum Hall state that has a Hall conductance of E squared over 2h. Okay, and so then what I want to do is I want to drill a little hole in the slab and thread a quantum of magnetic flux, just like in Laughlin's argument. And I want to think about what happens. Well, you know that since the surface is a quantum Hall state, that when you thread the flux, that there's going to be a flow of current out the surface, which is going to be exactly a charge of E over 2 has got to flow out the surface. Then it's going to flow around back into the other surface to here. Okay? And so what you know, therefore, is that along this flux line, a charge E over 2 actually has to be transferred from the bottom surface to the top surface. Okay, so that has to happen because, this is all non-interacting electrons. And so at the end of the day, after I've threaded the flux H over E, and everything's gapped, after I've threaded a flux H over E, there can't be any charge E over 2's around because this is all just non-interacting electrons. The only thing I could have is an E. Okay? And so in fact, when you thread an H over 2E flux through a topological insulator, in fact, a charge E over 2 is transferred between the top and the bottom surface. Okay? And so this is actually a sort of a fundamental property of a topological insulator. And one way of saying this, actually, is to ask, threading a magnetic flux through the topological insulator is sort of the same as taking a magnetic monopole and dragging the magnetic monopole from the bottom to the top. Through from the bottom to the top. And so this property is the same as saying that the charge of a magnetic monopole inside a topological insulator is E over 2. Okay, and so this is actually a famous effect, sometimes called the Witten effect, which is that when you have a theta term, that the theta term assigns charge to a magnetic monopole. Okay, and so basically the upshot of this, though, is that when you do this flux threading, a charge E over 2 is transferred from the bottom to the top. So now what I want to do is I want to say, let's suppose that we have some some state that doesn't break any symmetries, doesn't break time reversal symmetry, doesn't break it doesn't break charge conservation, and let's suppose, but it has a gap, and so let's imagine that we have that on the surface now. So now I'm going to do the same argument. I'm going to thread this magnetic flux, and then I can gauge it away, or I can think of it as dragging a magnetic monopole through. Okay? And so then it's still going to be the case that I transfer a charge E over 2 from the bottom to the top. Okay? But now, since I have a gap, and so when I thread the flux, since I have time reversal symmetry, there can be no Hall conductivity on the surface. So that charge just stays put, and it has to be left there at the end. And so in order for in order to have this gapped state, it must be possible to leave a charge E over 2 behind after you're finished. So that means that there have to be eigenstates of this system that have charge E over 2. Okay, and so this surface state, if you have a gap, must support these fractionally charged charge E over 2 excitations. Okay, so this is one argument that it has to be fractionalized. Another argument you can make is you can say, well, let's suppose I had this symmetry respecting gapped state. What would happen if I had a magnetic domain wall? So remember, on this magnetic domain wall, we have to have a chiral Dirac fermion. Okay? And so this chiral Dirac fermion has sort of like a Hall conductance of 1. It also has, it also carries heat. So there's sort of a central charge of 1 that occurs as well. Okay? So this is like just a chiral Dirac fermion. And so what has to happen if so now let's imagine that I put this symmetry respecting gap state in the middle. Then what has to happen is that this chiral Dirac fermion mode has to split in half. Okay, because the top half and the bottom half are really going to be the same as each other, and so half of it has to go this way and half of it has to go this way, and so this edge state has to have a Hall conductance of has to have a conductance of 1/2. But it has to have C equals 1/2. So it has to somehow split the chiral Dirac fermion into 2. So that means there has to be some chiral Majorana mode associated with this. Okay, and so having this Majorana mode means that this state has to also have some sort of non-abelian topological order as well. It has to be sort of like the Moore-Reed state of the fractional quantum Hall effect. Okay, and so it's an interesting problem to actually figure out what in detail this state looks like, and so this is something where there's actually been a lot of progress, and this actually is turning into a kind of interesting problem, which might be worth thinking about. But I'm out of time, and so I think with that I'm just going to finish. So thank you very much.
We have time for a couple of quick questions.
Pardon me? I'm sorry, does which state? Well, I'm assuming it does not. Yeah, so so obviously if I spontaneously break time reversal symmetry, then I'll be back to this. Okay, but I'm asking the question, could there be a state that does not break time reversal symmetry? Okay. I'm sorry, say. Yes? I'm sorry, say that again? So
if you had a boundary of a quantum spin Hall effect, it would be 2 plus 1D.
Like this, you're saying? Yeah, like this? Yeah.
So instead of putting this symmetry breaking terms, if you respect symmetry and then add some bad aspect that gaps these schedules. Can you do an analog thing of SRG in this?
Well, no. So look. So on this, I could imagine putting a time reversal symmetric term in my Hamiltonian, which backscatters a pair of electrons. Okay, and if that dominates, then you're right. I can get into a state where I have spontaneously broken the symmetry. But really, I would say that's really a state that's like this, where then I can I can have domain walls, if you will, between the different signs of the magnetization. And those domain walls are interesting because actually they bind a charge E over 2. It's sort of like the domain wall in the Sushri-Verheugen model. Okay, but that really is a spontaneous breaking of the symmetry. That's different than the kind of state that I'm that I'm trying to talk about here, where I'm assuming that I'm really not spontaneously breaking the symmetry. I don't know how to do the analog of this in the 2 plus 1 dimensional case. Yeah.
So naively, I think that if you combine any two distinct or different topological phases, you get some sort of a topologically protected edge state of some sort. But are there any general rules? I mean, the last slide you mentioned a couple of designs. I'm just curious if there's any like qualitative general rules for combining these different phases and looking at the interface.
Well, so certainly I think in the so for the free fermion cases, I think that's something that one can, yeah, there are general rules. Now, one has to revisit the problem when you allow for strong interactions, okay? And that's a very interesting thing to think about. And I think that is a subject which is not completely finished yet. Yeah.
Take one more.
Okay, yeah, yeah.
So for your TI superconductor devices, would it defeat the point if your superconductor is P-wave?
P-wave with that, just PX wave, not P plus IP. Well, so the problem with that is that you'd have nodes in your in the bulk, right? And so if what you're trying to do is make isolated Majorana modes, then those zero modes would couple to the nodal states in the bulk. So that would be a problem. Yeah.
But it would still be topological?
What?
Would it still be topological in a sense?
Well, so you would not have, so it doesn't have a gap.
Right.
So it's not, you know, if by topological we're talking about topologically classifying gapped states, then no, it's not. Though you know, you can think of the node itself. There's a sense in which that's topological. Okay, so if you have a nodal superconductor, then there's a sense in which you can think about whether the nodes of the superconductor are topologically protected. But that's a different issue than thinking about the topological insulator, which has protected boundary states. That's a different use of the word topological.
Okay, I think we can continue questions during the break and during lunch. Catch Professor Kane, he's around. And to thank Professor Kane, we would like to present him with the spaceship. It's a Star Wars Stormtrooper.
Wow.
Skyhawker, sorry, not Stormtrooper. To take you to far-off places and give you a change of scenery when you think about topological places.
All right, thank you.